Today we'll start this about the concept of field effect and the basic the structure of MOSFET. Okay, structure of MOSFET we'll see. Okay, structure of MOSFET. Structure of MOSFET. So sharing the screen. Okay, it's visible now. View response.
Yes,
Okay, yeah. So first, we need to see the concept of this field effect. Okay, concept of field effect. So what is this concept of field effect? Okay, so concept of field effect, if you see, so that means there is a resistance. You have a resistance R equal to what, rho L by A. Okay, R equal to rho L by A, and what is the, so this is resistance. Okay, this is resistance. Okay, resistance, and rho is nothing but resistivity. Okay, and next you have conductance. So conductance equal to 1 by resistance. So this is conductance. So conductance equal to 1 by resistance. So this is, you can write as rho L by A. Okay, rho L by A. 1 by rho L by. So you can write 1 by rho L by A. So this is equal to what? This is equal to A by rho L. Okay, A by rho L. So conductance equal to A by rho L. And there is a conductivity. Sigma is nothing but what? Conductivity. Okay, so conductivity and resistivity both are reciprocal with each other. So G, what I can write as G equal to 1 by rho, I can write as sigma A by L. Sigma A by L. Okay, sigma A by L. And we see in the drift current. Okay, drift current in the semiconductor physics, drift current equal to what? Sigma into E, no, where sigma is the conductivity. Sigma equal to n mu n, n mu n into n mu n into q plus p mu p into q. We already seen during semiconductor physics. Okay, so in general, what I can write, sigma equal to, for the, with respect to electrons, so this is n q mu into a, n q mu into a. So n is nothing but the charge carriers, and q is the charge of the electron, and mu is the mobility, and a is the only mu. Okay, so n q mu. Okay, sigma equal to n q mu. So from this I can write G equal to n q mu, A by L. Okay, A by L. Okay, so that means here, if you observe this relation, conductance is depends on the area of cross section. Conductance depends on the area of cross section. So that is there in JFET. Conductance is depends on the area of cross section, that is there in the JFET, and conductance is there in the depends on the charge carriers, number of charge carriers. Okay, so this is there in MOSFET. Okay, where conductance is depends on the area of cross section between the channel, that is nothing but JFET, and conductance is directly proportional to the charge carrier, that is there in the MOSFET. Okay, so what is this field effect? First, is this fine? Did you understood? Shall I move forward? Hello.
yes, sir, we got it.
Okay, next you see. So next, so concept of field effect, the variation of conductance of channel with respect to electric field. So what is the concept of field effect? Variation. So that means variation means what? Change. Variation means what? Change in conductance. Variation in conductance of channel with respect to what? With respect to electric field. With respect to electric field, that is nothing but we call as a concept of field effect. Okay, so that means whatever the transistor action is there, transistor action means what? Transfer of resistance, transistor action using field effect, using field effect. Okay, using field effect, that's why we call as field effect transistor. Okay, so if you consider the JFET, you have like we already studied JFET. Okay, so that means conductance depends on where area of cross section, variation in the area of cross section of channel. Okay, variation in the area of cross section of channel, area of cross section of channel, cross section of cross section of channel. Okay, cross section of channel. So and so that means variation of conductance is with respect to what? Variation of the area of the area of the channel. Okay, so like you already see in the JFET, like you have two gates are there. You already seen in the BTech, no, like two gates are there. So here like this is P plus, this is P plus, and this is N channel, and you are applying some gate voltage. Okay, you are applying some gate voltage by varying, already channel is there. Okay, already channel is there, you are applying some gate voltage, so that this whatever this depletion layer is there, you are varying. So if your depletion layer both touch each other, there is no movement of electrons from this from source to drain. Okay, so analogy means you can like you can take a tap. Analogy of operation of JFET is you can take the tap. Okay, so tap, if you take the tap, what, so here what is the, so what is the gate knob. Okay, so that means if you like so this tap example, so if you like if you rotate tap and anti-clockwise direction, inside the area will increase, whatever the water is there that is coming from drain to source, from the tank to this let us take bucket. Okay, so like bucket, suppose if you rotate that knob, the tap knob to towards clockwise direction, what happens, the area of cross section inside will decrease and it will stop the water. So like that, by applying the gate voltage, you are like you are varying the area of cross area between the channel. Okay, so area between the channel. So this we are not using for VLSI, this we are not using for VLSI. Okay, JFET we are not using. Okay, so we don't want this. Okay, whereas in MOSFET, if you see in MOSFET, we are, that means variation of carrier concentration, variation of carrier concentration, okay, of the channel, channel L. So that means by varying the carrier concentration, that is that means if it is P channel, you are varying the concentration of holes in the channel. If it is N channel, you are varying the concentration of electrons, okay. So by varying the concentration of carriers in the channel, we are varying the conductance. Okay, so that means by applying some external electric field. Okay, that varies the conductance, of the channel, okay, with applied electric field, with some applied electric field. Field effect is there, no? So with applied external electric field, so that means from this we can say that G is directly proportional to the concentration of charge carriers that is there in the MOSFET. Okay, this we are taking for VLSI. Okay, yes, is this fine? Shall I move forward?
Yes, sir.
So we are speaking with only MOSFET only, just JFET we are not speaking. Just JFET you already studied. So in JFET the conductance is directly proportional to the area of cross section of the channel, and in MOSFET the conductance is directly proportional to the charge carriers. Okay, concentration of variation of the by changing the charge carriers. Okay, by changing the charge carriers. Okay, so like so first enhancement NMOS. N MOSFET cross sectional view. Okay, cross sectional view. How enhancement cross sectional will you look like? Okay, so here NMOS, by seeing this NMOS, NMOS is how many terminal device? NMOS or NMOSFET. NMOSFET is it's a 4 terminal device. Okay, it's a 4 terminal device. So I will draw the 2D diagram. So 3D diagram means it will be a bit difficult. Okay, I'll share this image. You can go through that. 2D diagram I am drawing. So here this is cross sectional view. So you have a body. You have body. This is body, or we can call a substrate also. So this is body. Okay, body B. Okay, and P substrate. What is substrate? P substrate is nothing but it's a p-type material. Okay, p-type semiconductor, which is lightly doped, lightly doped. Okay, substrate is nothing but what? Lightly doped p-type semiconductor. Okay, and on the p-type substrate will diffuse two N plus. N plus means what? Heavily doped N plus regions. Okay, N plus, heavily doped N plus regions. Okay, and next here from here, this one and this one, there will be a insulator. This is nothing but SiO2, silicon dioxide. Silicon dioxide, and above this there will be metal. Okay, for gate you can use polysilicon also. Okay, this is nothing but metal. Above this silicon dioxide, you can use metal. For the gate you can use polysilicon also. Okay, polysilicon also. Okay, and here there is a metal. This is also metal, and this is also metal. Okay, so now this is what? This is source. And this one is drain, and this one is gate. And if you see, so this is channel region. Okay, channel region, and this is the length of the channel. Now they are talking about in VLSI technology, no? So technology is nothing but we can call as length of the channel. Length of the channel is nowadays they are making the chip with nanometer technology. They are making the chips with nanometer technology. Okay, so this is how many terminals? So from this I can say, so here it's a NMOS is how many terminal device? How many
4 terminal.
4 terminal device. Okay, 4 terminals you have. What is first one? Source. Okay, source is nothing but N plus diffusion, highly doped N plus semiconductor will be there. And next you have drain is N plus diffusion, and next you have gate is MOS structure. MOS structure is nothing but what? Metal-Oxide-Semiconductor. So without if you consider without source and drain, that we call as MOS. MOS means what? So this is metal, and this is oxide, and this is semiconductor. So this is like a MOS structure, Metal-Oxide-Semiconductor. So that means MOS structure means what? Metal. I told you, no, for gate we can use polysilicon also. Okay, we can use polysilicon also. And next oxide. So basically we are using SiO2 as a oxide, which is having high dielectric, high dielectric. It is acting like a capacitor also. Suppose if you consider a capacitor, here you see, so positive charges and negative charges will be there. Positive charges, in between there will be a dielectric. That means this is one terminal. Okay, and this is another terminal. In between there will be a dielectric. That means here MOS capacitor. We can call as MOS capacitor also. Okay, and next next you have bulk or three names are there: body or substrate. Bulk, body or substrate. This is what p-type semiconductor, lightly doped p-type semiconductor. Bulk, body or substrate. Okay, so source, drain, gate, next gate and the bulk. These are the four terminals. Is it fine?
Yes, sir.
Okay, I'll move forward. So next you see, next what is a channel? What is a channel? Okay, channel, channel. Okay, channel is nothing but so how the channel is formed. This is the induced. What is meant by induced? That is what internally developed. Internally developed. Induced means what? Internally developed. So internally developed with external field. With some external field, it is internally developed. Okay, external field. Okay, so what is a channel? Channel is nothing but a thin layer. Yesterday I told you, no, thin layer of carriers. Thin layer of carriers. So that means this is a thin layer. This is nothing but channel. Okay, so channel. So that means here some electrons are flowing. Okay, electrons are flowing. This we call as N-channel. N-channel. Suppose thin layer is there. Here some holes are flowing. Okay, some holes are flowing. Okay, holes are flowing. We call as P-channel. P-channel. Okay, so where it will be there? On the surface of the substrate. On the surface of the substrate. Surface of the substrate. So if you see where the channel area, I already shown the channel area. Okay, see here, this is channel. Where is the channel area? This is the channel region. So where it is located? On the surface of the substrate. Okay, on the surface of the substrate the channel is there. Okay, and it is there in between. Where it is there? In between the source and drain. Between the source and drain. Okay, and channel length. What is channel length or gate length? That is denoted by L. So okay, L is nothing but what we can call as channel length, or we can call as gate length. Channel length or gate length. Okay, so see here. So that means here, so on the surface of between the, so where it is there, that is between the source and drain. Between the source and drain. Source and drain, and channel length. Channel length, or we can call as gate length. Gate length, channel length or gate length, that is denoted by L. Denoted by L. Okay, so enhancement MOSFET. Enhancement MOSFET means what? There is no channel. Okay, we need to develop the channel. That is nothing but enhancement MOSFET. Depletion MOSFET is nothing but already channel exists. That can be operated in both depletion and enhancement mode. Okay, first we will study about what is this enhancement mode, N-channel MOSFET. Next, enhancement P-channel MOSFET, and depletion N-channel MOSFET, and depletion P-channel MOSFET. Okay, first today we will see about one operation, that is cutoff region. We will see. Okay, only cutoff region we will see. Okay, every day we will study about one operation, so that you can understand very well. Operation of enhancement and MOSFET. Operation of enhancement and MOSFET. Okay, what is this operation? Okay, first operation today we'll see cutoff region. So what is this cutoff region? We'll see. Okay, so cutoff region. So here I am drawing this MOSFET. So this is N plus, and this is one more N plus, P substrate, P substrate, and this one is SiO2 layer, okay, and this one is polysilicon or metal or polysilicon, okay, and this is metal, and this is one more metal. Through the metal contacts you need to give it to source and drain, okay. So this source is there, source is connected to ground. This source terminal is connected to ground, and gate terminal also you need to connect to ground, and drain terminal also you need to connect to ground, okay, ground. And this bulk is there, no, bulk or body, and this source are uh, shorted, okay, are shorted, okay. So it's look like what, it's look like, suppose see here, it's look like two PN junction connected back to back, no, P2, this is N, so two PN junction diodes, this is P, next this is one more PN junction diode connected back to back, okay. It's look like like this, that means two PN junction diodes, connected back to back. Here it is given to which one, this is drain, okay, this is drain, and here you will get a source, okay. So what is the condition for cutoff region? That means VGS is nothing but gate to source voltage, and VDS drain to source voltage, and next VSB, that VSB is nothing but what, source to bulk or body voltage, that is equal to what, 0, okay. So 0 means what, you are all the terminals we are connecting to ground, okay. It will act as what, it will act as reverse bias PN junction diode, it will act as reverse bias PN junction diode, okay, PN junction diode. From where to where? Between the source and bulk, source bulk, and drain bulk, okay. So two PN junction diodes connected back to back. So when two PN junction diodes are connected back to back, what happens? So we already seen, that means in the PN junction diode, when this is reverse bias, there is no current, there is less amount of current, that is due to minority carriers, okay. So that means here in reverse bias PN junction diode, there is high resistance will be there, okay, high resistance, okay. So due to this high resistance, what happens? High resistance, there is no flow of charge carriers, no flow of charge carriers. So if there is no flow of charge carriers, there is no drain current. ID equal to what? 0, okay. So there is no flow current, and so that means there is no flow of charge carriers. Charge carriers means either it may be electrons or holes, so there is no drain current, okay, no drain current. So that means here no drain current. In which region? Cutoff region. No drain current in cutoff region, okay. So this is the operation of enhancement MOSFET in which region? This is first region, that is cutoff region. So basically we have like first you have region of operations are there. So like first cutoff region we already seen, cutoff region, okay. And next you have linear region, and next you have non-linear region. Linear region and non-linear region we call as a triode region. This you remember, triode region. Linear and non-linear region we call as triode region, and saturation region, okay. And one more pinch off point is there, pinch off point, okay. And one more, this is not region, this is the condition, channel will be pinched off, or channel punch through, channel, these are the words we use, channel punch through or reach through, reach through. This we will discuss, don't worry. This we will discuss what are these pinch off condition, punch through or reach through. These are the operations. In these operations we discussed now which region, cutoff region. Okay, so which region, cutoff region. Okay, and so what happens, that cutoff region is there, and next, so is it fine, cutoff region? Shall I move forward?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Yeah, next you see, so next what I am doing, I am using VSB equal to 0. Okay, VGS, I am applying small amount of positive voltage. Okay, small amount of positive voltage. Okay, small amount of positive voltage, and VGS is less than VT. VT is nothing but threshold voltage, and VDS equal to 0. Okay, VT is nothing but a threshold voltage. Okay, VT, threshold voltage. So what happens, here I am drawing the circuit. So this is P substrate, N plus and N plus, and SiO2 layer, polysilicon, and this is metal, this is polysilicon. Okay. So anyway, like basically we'll call as a 3-terminal only. Every time source is connected to bulk. Okay, source is connected, this is source is there, no, source is connected to, basically this is 4-terminal device, but source is connected to body. Okay, source is connected to body. Okay, so here what you are giving, that means you are giving small amount of gate voltage. Let us take, this is gate voltage, you are applying small amount of gate voltage. Okay, so here with respect to source ground, no, so with respect to source means this is nothing but we can call as VGS. Okay, VGS is what, greater than 0. Okay, VGS is greater than 0, and we are not applying VDS voltage, so anyway this is connected to ground. Okay, so VDS, so with respect to drain and source, so we are applying VDS equal to 0 only. Okay, VDS equal to 0 only. So what happens, here we are applying positive voltage, to the gate, What are the majority carriers in the p-type substrate? Holes. Okay, so here you are applying positive voltage, these holes will, what happens, these holes will repel, due to this like charges repel, no, like charges repel, the holes will repel. Okay, and what are the majority carriers, what are the minority carriers? Electrons are there, no, so electrons, what these electrons will do, electrons will attract, so these electrons will attract, due to here there is a insulator. Okay, due to this insulator, this will not go into this positive charge, this will be available in the surface of the substrate, Okay, so that means what I can say, that means when you apply positive gate voltage, that means VGS is greater than 0, small value of VGS we are applying, there is a repulsion of hole from the surface of substrate, repulsion of holes, okay, on the surface of substrate. Why? Because you applied the positive voltage. Okay, and there is a depletion layer, so that means depletion layer will be formed. Initially there is a depletion layer is there, that is more towards where p-type substrate. Okay, in p-n junction diode also we already seen, just you imagine the operation of p-n junction diode. p-n junction diode under no bias condition, what happens, there will be a depletion layer, no, there will be depletion layer here, what negative ions, here positive ions, due to this immobile ions, there will be a depletion layer formed between p and n. We already discussed, no?
Yes, sir.
So here also p-n junction diode is there, here this is heavily doped and p-type substrate is lightly doped. So due to this lightly doped, the depletion layer is towards the p-type substrate, So it is more towards the p-type substrate. Okay, and what happens due to which ions means acceptor ions. What are the acceptor ions? Negative ions. Acceptor ions. Okay, depletion layer is due to acceptor ions. Okay, and next there is an inversion, so depletion layer will be formed. Depletion layer is formed. Okay, layer is formed due to acceptor ions. Okay, and there is a inversion layer also. There is a inversion layer also. What is inversion layer? What is inversion layer? So that means this is a inversion layer. Basically this is which type of which type material?
P.
P-type material. So in P-type substrate, in P-type semiconductor, you are so there is a formation of electrons. That means N-type like material is forming. In N-type, so in P-type, what are the majority carriers? Holes are the majority carriers. But what happens in P-type semiconductor? There is N-type means majority carriers are nothing but electrons are forming in this. Electrons are forming in this. N-type material like is forming. Okay, due to what minority carriers are attracted toward this positive charge. Okay, that is nothing but inversion layer. Okay, inversion layer forms. Inversion layer forms as what electrons. Okay, the minority, so how inversion layer is formed? As you apply positive voltage, majority carriers will repel, and the minority carriers, whatever the minority carriers are there, minority carriers will get attracted. Minority carriers will get attracted. Did you understood what is this depletion layer, repulsion of holes?
Yes.
What is inversion layer?
Yes, sir.
Okay. So here we want to see the some definitions of this. What is inversion layer, weak inversion layer, strong inversion layer. Okay, and threshold voltage. You need to see. You need to know about these definitions. Okay. So now I told you the inversion layer. What is inversion layer?
Which is formed due to minority carriers.
Inversion layer refers to what? Inversion layer, that is refers to what? Refers to conversion of p-type surface, p-type surface to n-type like. In the p-type surface, what happens? In the p-type surface, here the electrons are forming. It is forming like a n-type. Okay, that is nothing but inversion layer. Okay, that is nothing but inversion layer. And in inversion layer there are two types. One is weak inversion layer and strong inversion layer. Okay, so there are two types are there: weak inversion layer and next is strong inversion layer. Okay, weak inversion layer and strong inversion layer. So what is weak inversion layer? Weak inversion layer is nothing but, suppose the concentration of electrons in the surface of substrate. Okay, the concentration of electrons in the surface of the substrate, that means concentration of electrons in the surface of substrate is less than the concentration of holes in the p-type substrate. Okay, is substrate, then we call as what? Weak inversion layer. So that means from here I can say that what is weak inversion layer? Here the concentration of electrons in the surface of substrate are less than the concentration of holes in the p-type substrate, then we call as p-type, that is weak inversion layer. Okay, that is nothing but weak inversion layer. Okay, so the concentration of electrons in the surface of substrate is less than the concentration of holes in the p-type substrate, that is nothing but weak inversion layer. Okay, and next strong inversion layer. So strong inversion layer is nothing but what? There is, that means here in the strong inversion layer, what happens? Here you are applying what? So VGS means what? Negative with respect to what? Source. With respect to gate you are applying positive. Okay, here what are the majority carriers in N plus? Electrons, no?
Electrons. Yes,
Electrons.
sir.
So due to this negative, what happens? Enough number of electrons are pulled from where to where, n plus. So here electrons will be repelled. Electrons will be
Repel.
repelled. So that will be added in this channel. Electrons will be repelled in the added in the channel. Okay. So with respect to source and drain, here with respect to source and drain, enough number of electrons are added in the channel. Okay. So at one condition, what happens? The concentration of electrons in the surface of substrate, those are equal to the concentration of holes in the p-type substrate. Then we call a strong inversion layer, or we can call as a channel region. That is nothing but channel region. Okay. That is nothing but strong inversion layer. Okay. So that means here I can write. So this is very important. What is weak inversion layer? What is strong inversion layer? Or channel? Or they will ask channel region. Channel region. Okay. So what is this channel region? That means here enough number of electrons. Enough number of electrons will be number of electrons pulled from n plus source. Okay. So what is the condition? So the concentration of electrons. Okay. The concentration of electrons in surface of substrate, that is equal to concentration of holes in p-type substrate. Okay. Then what happens? Strong inversion layer will be formed. Okay. So that means concentration of electrons in the surface of substrate equal to the concentration of holes okay, in p-type substrate. Then there is a strong inversion layer, or we can call as channel region. Okay. So that is a weak inversion layer and strong inversion layer. Okay. And next you have threshold voltage. So what is this threshold voltage? This is nothing but Vt. Threshold voltage is Vt. Okay. This is nothing but how much of minimum voltage. Okay. Minimum gate voltage. Okay. So in enhancement MOSFET, you are applying VGS as positive or negative?
Positive.
We are applying positive. Okay. Gate voltage as positive. Minimum gate voltage we are applying to create a strong inversion layer. Or we can call as channel. That is nothing but threshold voltage. Okay. So that means VGS should be, when channel will form, VGS should be greater than VT, then only channel will form. How much of minimum gate voltage we are applying, such a way that you are getting a strong inversion layer, that is nothing but we call as channel. Okay. Is it fine? So today we discussed about so today we discussed about this field effect of field. Okay. Field effect, electric field is nothing but what? Suppose we are applying in semiconductor physics, we already studied E equal to minus del V, you got now. E equal to minus del V. Okay. Minus del V. That means suppose this is a like semiconductor physics. PN junction diode. Let us take PN junction diode. You are applying some external voltage. So that means the voltage with change in length of the conductor, length of this, okay, with respect to length, is nothing but electric field. So E equal to what? Minus dV by dx. Let us consider the length is x. Okay. So minus del V, that is x, that is electric field. Okay. So we seen the relationship between the resistance, conductance, and resistivity, conductivity. Okay. And we got conductance is directly proportional to area of cross section, that is related to JFET. Conductance is directly proportional to the concentration of charge carrier that is there in the MOSFET. JFET we are not preferring in our VLSI, we are preferring MOSFET only. Okay, that too we are preferring enhancement MOSFET. Okay, that too depletion MOSFET also we are not giving. Why? Because channel already exist. Okay, channel already exist. Already some charge carriers are there in the channel. We are applying some external voltage so that we are controlling the charge carriers. Okay, we are applying some external power supply so that some application they can use, but mostly like making these ICs and this VLSI related thing, we need to take care of this power related issues also. We should take low power. So why we need to do extra power to control the charge carriers? Okay, that is in the depletion type MOSFET. Okay, so here in enhancement MOSFET what we are doing, we are like channel is not there, so what we are doing, just we are applying the external voltage so that internally we are developing the channel. Okay, so this is the two-dimensional view of enhancement MOSFET. This is 4 terminal, source, gate, drain and body. Okay, p-type substrate is lightly doped and n plus is heavily doped, and there is induced channel. Induced means internally developed, that is a channel is nothing but what is a channel? Okay, it's a layer of carriers where it is forming. Okay, it is between the surface of the substrate and in between the source and drain. Okay, and there is a gate length or channel length that is denoted by L. Okay, so this is the operation of cutoff region. Okay, so all the voltages you need to give it to 0. It's like a 2 p-n junction diode connected back to back. Okay, so how many regions it is operated by? 4 regions: cutoff region, linear region, non-linear region and saturation region. Today we discussed about cutoff region, and we discussed about some layers. Okay, if you apply some positive voltage, okay, this is the condition, source to bulk voltage is 0 and VGS is greater than 0. Small value of VGS we are applying. What happens, what are the majority carriers are there that will be repelled, and minority carriers are there that will be attracted. Okay, and there are 2 types of layers will be formed. One is weak inversion layer and strong inversion layer. What is weak inversion layer? The number of electrons present in the surface of the substrate is less than the number of holes in the p-type substrate, that is weak inversion layer. Strong inversion layer or channel region is nothing but what happens if you increase more and more gate voltage, gate to source voltage, more electrons will be pulled. Okay, why? Because for the source we are applying negative voltage, so this will be pulled. So what happens, the number of electrons in the surface of the substrate becomes the equal to the number of holes in the p-type substrate. Then we get a strong inversion layer. Okay, or channel region. Okay, so due to this number of electrons in the surface of substrate equal to number of holes in the p-type substrate. Okay, and there is a threshold voltage. Threshold voltage is minimum gate voltage, positive voltage we are applying to create a strong inversion layer or channel is nothing but threshold voltage. Okay, that is the threshold voltage. Okay.
Yes.